Hi everyone, today I'll be talking about seeing the unseen, visual common sense for semantic placement. This work was done in collaboration with Georgia Tech and AI2. In this work, we study how to learn visual reasoning models that can predict semantically meaningful locations to place objects in indoor environments. Consider asking a person where I can put cushions in the living room. People can reason about correct receptacles to place the cushion, armchair, and couch in this case, and for that the cushion should go on armchair to maximize comfort as the couch is already full. Similarly, if the visual context changes, we can now say that the cushion should go on the couch either in the center or on the right side of the armrest. Learning this form of visual reasoning is critical for various applications like building tidying robots that can clean your house, to AR systems that can help you visualize your own furniture with preferred aesthetics in a new home. To study this problem, we propose semantic placement, a new CV task where a vision system is given an image and a target object category, and it's tasked with placing semantically meaningful regions to place objects in the image space. Traditional CV tasks are focused on localizing, describing, and classifying what is already visible in the image. However, SP requires you to reason about what is not visible in the image by leveraging scene context. Learning the invisible is hard, there are no existing datasets for it, so how can we learn such a vision system? To curate such a dataset for learning SP, we take advantage of the observation that the images on web already have objects placed at semantically meaningful locations. Now all we need is the state of the environment without that object in it. This can be achieved by simply removing objects using in-painting models. With this, now we have paired states of the environment with and without the objects at a certain location. We can then use original detections as the target labels for learning semantic placement in a supervised manner. We propose a two-stage training approach where we first train our SP model using synthetically curated SP dataset from real images from Lion, and then fine-tune it using programmatically generated simulation data where you don't have any artifacts. Our data generation pipeline consists of following stages. First, we use Detic and SAM to detect and localize objects of interest. Next, using SAM masks an original image, we in-paint the objects using in-painting models. Next, we filter out the images where in-painting failed using a 2D instance matching filter. Finally, we generate augmented version of in-painted images using different textures with different diffusion models and use it for training. We do this to mitigate overfitting to artifacts of in-painting. Here's an example of an image generated using our data pipeline. Using this pipeline, we collect total 1.3 million images across 9 object categories. We also leverage Habitat Simulator and 200 Habitat Synthetic Scene dataset scenes to build high quality synthetic dataset free of artifacts for fine tuning, which consists of 80K images for training and 20K images for validation. We propose a simple model architecture that leverages frozen clip image and text encoder and learns a unit decoder on top of it using dice loss with heavy augmentation to do semantic placement predictions. We compare our method against 3 baselines that leverage LLMs and VLMs. Our LLM baseline first uses target object category and LLM to query valid receptacles for each object category, then uses open vocab detector such as Detic to detect receptacle surfaces where you can place an object. For VLMs, we prompt the VLMs using the image and a text prompt asking it to localize object placements as bounding boxes. We do this for both GPT-4V and Lava and have separate prompts for each. To compare performance of these methods, we propose 3 quantitative metrics and do human evaluation. For human evaluation, we show that each MTurk worker predictions from 5 models and ask them to rank them from most preferred to least preferred. We report percent times each model was ranked first as our human preference metric. For details on additional quantitative metrics, please check out our paper. We find our proposed method outperforms all 3 baselines on human preference by 23% on real-world images and 2.4% on HSST images. Here are few qualitative examples of our predictions from Lion SP and HSST val images. These examples show our model is able to effectively learn semantics of precise object placement, like vases go on the center of coffee table, books go on bookshelves, and desks, and cushions go on couches. Next, we demonstrate application of SP models on downstream task of embodied semantic place, where an embodied agent is tasked with placing an instance of an object on a valid receptacle precisely, in this case, a pillow. This agent is evaluated based on how accurately it placed the object at its position on a certain receptacle. Our ESP policy solves task in 2 stages. First, we leverage frontier exploration and semantic placement masks to build a Semantic placement guided affordance map of the environment. Once the agent has explored the environment to a sufficient degree, we use the fast marching based navigation planner to go to closest placement location indicated by the map. Once the agent reaches close enough to the placement region, the control is handed off to a placement policy that uses semantic placement predictions from the model on the head camera and samples points on the predicted regions, projects them to 3D, and samples a placement location that is then realized using a IK planner. We evaluate ESP models for three SP models: LLM plus detector, Lava, and clip unit. We do not evaluate GPT-4V due to high number of API call requirements. We find our method clip unit outperforms both the baselines by achieving 12.5% success rate on ESP task. After analyzing the failure modes, we find majority of failures come from failure in navigation around clutter or precise object placement, and failures due to invalid SP masks are relatively low for our method. Please check out our paper for more details on the analysis. Here's a qualitative example of agent placing a cushion in the living room. The video shows the third person observation of the agent followed by SP masks and SP affordance mask map being built online. As you can see, the agent successfully navigates to a couch solely using SP masks and samples a placement location next to the armrest in front of other cushions. Key takeaways from our work are: we propose a novel visual common sense reasoning task called semantic placement. We show synthetic dataset can be curated for such tasks by leveraging vision foundation models can help learn effective SP models. Finally, when deploying these models for downstream tasks like tidying robots, precise control and fine-grained navigation are quite challenging. Thanks for listening. Read more about the paper on our website.